We just found something that shouldn't exist. Something so massive, so incomprehensibly large, that it breaks our understanding of how the universe works. And I'm not being dramatic here. This discovery literally violates the cosmological principle, which is basically the foundation of modern cosmology. Imagine if you found out that gravity doesn't work the same everywhere, or that the speed of light changes depending on where you are. That's the level of, wait, what, we're dealing with. This thing is called the Hercules-Corona Borealis Great Wall. But honestly, that name doesn't do it justice. We should call it the thing that shouldn't be here, or the universe's biggest plot twist. Because here's the deal. According to everything we know about physics, structures this large simply cannot form. The universe isn't old enough. There hasn't been enough time. It's like finding a fully grown oak tree that's somehow only 3 days old. And yet, there it is, sitting 10 billion light years away, mocking our understanding of cosmology. But before we get into why this thing is so mind-blowing, we need to talk about what it actually is. And to understand that, we need to go on a journey through cosmic structures, starting small and working our way up to the absolutely ridiculous. Buckle up. This is going to get weird. Part 1, the cosmic ladder, from planets to universe-breaking walls. Let's start with something familiar, Earth. Earth is about 12,742 kilometers in diameter. That's our baseline. That's what we know. Now, the Sun is about 109 times wider than Earth. So already, we're at a scale that's hard to visualize. If Earth were a marble, the Sun would be a beach ball. But the Sun is nothing. It's not even a particularly large star. Betelgeuse, the red supergiant in Orion, is about 700 times larger than the Sun. If you put Betelgeuse where our Sun is, it would extend past the orbit of Mars. Earth would be inside the star. But stars are just the beginning. Stars cluster together into solar systems. Our solar system is about 287 billion kilometers across if you count the Oort cloud. That's already a number so large it's meaningless to our brains. Multiple star systems form neighborhoods in the galaxy. Our local neighborhood, called the local bubble, is about 300 light years across. That means light, traveling at 300,000 kilometers per second, takes 300 years to cross it. We're scaling up fast now. Our galaxy, the Milky Way, is about 100,000 light years across and contains 200 to 400 billion stars. Each of those stars might have planets. The sheer number of worlds in just our galaxy is staggering. But the Milky Way isn't alone. It's part of the local group, a collection of about 80 galaxies spanning 10 million light years. The local group is part of the Virgo supercluster, which contains about 100 galaxy groups and clusters, spanning 110 million light years. And the Virgo supercluster? That's part of Laniakea, a supercluster of superclusters containing about 100,000 galaxies across 520 million light years. At this point, we're dealing with structures so large that light from one end takes 500 million years to reach the other end. But we're still not at the top, because galaxies and superclusters aren't distributed randomly. They form an even larger structure called the cosmic web. Part 2, the cosmic web, the universe's skeleton. If you could zoom out and see the entire observable universe at once, you'd see something that looks disturbingly like biological tissue or neurons in a brain: the cosmic web. Galaxies aren't scattered uniformly through space. They're arranged in filaments, sheets, and clusters with enormous voids between them. Think of it like this. Imagine a kitchen sponge. The solid parts are where galaxies cluster along filaments. The holes are voids, vast regions of nearly empty space. These filaments can stretch for hundreds of millions of light years. Galaxies flow along them like blood through veins, pulled by gravity into denser regions where they cluster together. The voids between the filaments are the emptiest places in the universe. Some are 150 million light years across, with almost no galaxies inside them. Just emptiness. This structure formed from tiny quantum fluctuations in the early universe. Right after the Big Bang, space wasn't perfectly uniform. There were regions that were slightly denser than others. And I mean slightly, like 0.001% denser. But gravity amplifies tiny differences. Denser regions pulled in more matter, becoming even denser, pulling in even more matter. Over billions of years, this created the cosmic web we see today. It's like a snowball effect, but instead of snowballs, you're dealing with galaxy-sized clumps of matter, and instead of rolling down a hill, they're collapsing under their own gravity over billions of years. Computer simulations of the early universe predict this structure perfectly. We run the equations forward from the Big Bang, and out pops the cosmic web. The match between prediction and observation is so good, it's one of the major confirmations of our cosmological model. The largest structures in this web are galaxy filaments and walls, vast sheets of galaxies forming the boundaries of cosmic voids. And this is where things get interesting, because there's a limit to how large these structures should be. Part 3. The cosmic speed limit, and it's not the speed of light. Here's something that blew my mind when I first learned it. There's a maximum size that cosmic structures can reach, and it has nothing to do with the speed of light. It's called the homogeneity scale, and it's about 1.2 billion light years. Above this scale, the universe should look roughly the same in all directions. Structures should average out. It's like zooming out on a pointillist painting. Up close, you see individual dots, but from far enough away, it all blends into a uniform image. This is the cosmological principle, the idea that on large enough scales, the universe is homogeneous, the same everywhere, and isotropic, the same in all directions. This principle isn't just a nice idea, it's fundamental to cosmology. Einstein's equations for general relativity, the Big Bang model, our understanding of cosmic expansion, all of it assumes the cosmological principle is true. If the universe weren't homogeneous at large scales, nothing works. The math breaks down. Our models don't make sense. So when we say structures shouldn't exist above 1.2 billion light years, we're not just saying they're unlikely. We're saying they violate the basic principles that make our cosmological models work. Why 1.2 billion light years specifically? It has to do with how fast structures can grow. Remember, structures form when denser regions pull in surrounding matter through gravity. But this process takes time. The universe is about 13.8 billion years old. In that time, matter has only had so many opportunities to clump together. Even under the most favorable conditions, there's only been enough time for structures to grow to about 1.2 billion light years across. anything bigger than that, and you're implying either A, the universe is much older than we think. It's not. We've measured this very precisely. B, structures can form faster than gravity should allow. They can't. We understand gravity very well. C, the cosmological principle is wrong, and the universe isn't homogeneous at large scales. Uh-oh. So finding a structure larger than 1.2 billion light years is like finding a tree that's taller than physics says it should be able to grow. It suggests something is wrong with our understanding. Now, guess what we found? Part 4. Enter the Great Walls. In 1989, astronomers Margaret Geller and John Huchra discovered something shocking. They were mapping the positions of galaxies, creating a 3D map of cosmic structure, and in their data, they found a massive filament of galaxies stretching across 500 million light-years. They called it the CFA2 Great Wall, after the Harvard-Smithsonian Center for Astrophysics where they worked. 500 million light-years. That's big, but it's under the 1.2 billion light-year limit. Unusual, but not physics-breaking. Then in 2003, we found the Sloan Great Wall, 1.37 billion light-years long. Uh-oh. That's over the limit. That's bigger than structures should be able to grow in the age of the universe. Cosmologists were concerned, but not panicking. Maybe the limit was slightly higher than we thought. Maybe there were some special conditions that allowed this one structure to form. Outliers happen, right? Then we found more. The huge LQG, Huge Large Quasar Group, in 2012, 4 billion light-years across. The giant GRB ring in 2015, 5.6 billion light-years across. And then, the big one, the Hercules-Corona Borealis Great Wall, 10 billion light-years across. Let me put that in perspective. Light from one end of this structure takes 10 billion years to reach the other end. That means when light left one end of this structure, Earth didn't exist yet. The sun didn't exist. Most of the stars you see in the night sky didn't exist. The light started its journey when the universe was only about 3.8 billion years old, barely a quarter of its current age. This structure is so large that it spans 10% of the observable universe's diameter. It's not just breaking the cosmic speed limit, it's obliterating it. Part 5. What even is the Hercules-Corona Borealis Great Wall? Let's talk about what this thing actually is, because Great Wall is kind of a misleading name. It's not a solid object. You couldn't fly a spaceship into it and crash. It's more like a region of space where there are a lot more gamma-ray bursts than there should be. Wait, gamma-ray bursts? Let me explain. Gamma-ray bursts, GRBS, are the most energetic explosions in the universe besides the Big Bang itself. They happen when massive stars collapse into black holes, or when neutron stars merge. For a few seconds, a gamma-ray burst can outshine the entire observable universe. It releases more energy in 10 seconds than the sun will produce in its entire 10 billion year lifetime. They're so bright, we can see them from billions of light years away. Since the 1990s, we've been detecting and cataloging these GRBs. And because we know how far away they are, we can map their positions in 3D space. In 2013, astronomers Istvan Horvath, John Hakala, and Zsolt Bagali were analyzing this GRB data when they noticed something weird. there was a region of space where GRBs were clustering. A lot. At first, they thought it might be a statistical fluke, but they ran the numbers. The probability of this clustering happening by chance was about 1 in 20,000. Not impossible, but very unlikely. They kept analyzing, adding more data. The pattern held. There was definitely something there, a massive concentration of galaxies, because GRBS come from galaxies, forming a structure. They measured it, then measured it again, 10 billion light-years across. They published their findings, and the astronomical community went, wait, what? Because this wasn't just slightly over the limit. This was more than 8 times larger than structures should be able to get. Part 6, the math doesn't math. Let's talk about why this is such a problem. Structure formation in the universe is well understood. We can model it with computers, run simulations, and the results match what we observe. Usually, the process goes like this. 1. Early universe has tiny density fluctuations, quantum fluctuations stretched by inflation. 2. Denser regions have slightly stronger gravity. 3. They pull in surrounding matter, becoming denser. 4. Now their gravity is even stronger. They pull in more matter. 5. Repeat for billions of years. 6. You get the cosmic web. We can calculate how fast this process happens. We know the age of the universe, 13.8 billion years, the density of matter from measurements, the strength of gravity very well tested, the initial fluctuation sizes from the cosmic microwave background, plug it all into the equations, run the simulation, and out comes a maximum structure size, about 1.2 billion light-years. Structures bigger than this require more time than the universe has existed, unless something's wrong with our assumptions. Maybe the early universe wasn't as uniform as we think. Maybe there were larger fluctuations in some regions. But we've measured the cosmic microwave background, the afterglow of the Big Bang, to incredible precision. We can see the fluctuations. They're tiny and uniform, exactly as predicted. Maybe gravity works differently on these scales? But we've tested general relativity extensively. It works perfectly from solar system scales up to galaxy cluster scales. Why would it suddenly change at supercluster scales? Maybe the universe is older than we think? Nope. We've measured the universe's age through multiple independent methods. They all agree 13.8 billion years, give or take 100 million. Maybe structures can form faster if matter is distributed just right. Possible, but we'd need a very specific, very unlikely arrangement. And we've found multiple structures over the limit. The Hercules-Corona Borealis Great Wall is just the biggest. If special conditions are required, why do we keep finding these things? The honest answer is, we don't know. This is a genuine crisis in cosmology. Our models are very good. They predict the cosmic microwave background, the abundance of elements, the expansion rate of the universe, the large-scale structure, everything, except these giant structures. Part 7, the quasar connection. Now, let me introduce you to another piece of this puzzle that makes everything even weirder: quasars. Quasars are supermassive black holes actively feeding on matter. As matter spirals into the black hole, it heats up to millions of degrees and emits enormous amounts of radiation. A single quasar can outshine an entire galaxy of 100 billion stars. They're among the brightest objects in the universe. which means we can see them from very far away. Most of the quasars we detect are billions of light years distant, showing us what the universe looked like billions of years ago. And here's the interesting part. Quasars cluster. They're not randomly distributed. They tend to be found in regions where matter is denser, the same regions where we find galaxy clusters and filaments. In 2012, astronomers discovered the huge LQG, Huge Large Quasar Group. It's a collection of 73 quasars spanning 4 billion light-years. 4 billion light-years. That's already 3 times larger than the theoretical limit. The probability of 73 quasars clustering this tightly by random chance is basically zero. Something caused them to group together. That something is gravity, pulling matter into a massive structure. Then in 2019, astronomers found an even bigger quasar group, and another, and another. Quasars seem to trace out these enormous structures that shouldn't exist. It's like they're marking the skeleton of universe-sized buildings that physics says can't be built. The Hercules-Corona Borealis Great Wall was actually discovered through gamma-ray bursts, not quasars. But the principle is the same: extremely distant, extremely bright events clustering in ways that reveal underlying structure, and these structures keep getting bigger. Part 8: Alternative explanations and why they don't work. Okay, so we've got structures that violate our models. Let's talk about possible explanations. Explanation 1: it's a statistical fluke. Maybe we're seeing patterns that aren't really there. Humans are really good at finding patterns, even in random data. The problem? We've done the statistics rigorously. Multiple independent teams have analyzed the data. The Hercules-Corona Borealis Great Wall's existence is statistically significant at the 99.995% confidence level. That means there's only a 0.005% chance this clustering happened randomly. Could we be that unlucky? Sure, but we've now found multiple structures over the limit. At some point, you have to stop saying bad luck and start saying maybe our model is wrong. Explanation 2: it's a projection effect. Maybe we're seeing multiple smaller structures that happen to line up along our line of sight, making them look like one giant structure. This is actually possible. Space is 3-dimensional, but we observe it from one viewpoint, so structures at different distances can appear to overlap. The problem? The gamma-ray bursts forming the Hercules-Corona Borealis Great Wall are all at roughly the same distance from us. They're not just lined up from our perspective, they're actually at the same place in the universe. We can measure this using redshift, how much the light has been stretched by cosmic expansion. All the GRBs in the structure have similar redshifts, meaning they're at similar distances. Explanation 3: our structure formation models are slightly wrong. Maybe structures can grow a bit faster than we think. Maybe we're missing some physical process that allows larger structures. The problem? Our models work really well for everything else. They correctly predict the cosmic microwave background pattern, the abundance of elements, galaxy formation, cluster formation, the cosmic web's overall structure. If we change the models to allow 10 billion light-year structures, we break all these other predictions. It's like trying to fix a small leak by knocking down a wall. Explanation 4: the cosmological principle is wrong. Maybe the universe isn't actually homogeneous at large scales. Maybe there are regions that are. fundamentally different from other regions. This is the nuclear option. If true, it means most of our cosmological models need to be revised. Einstein's cosmological equations might need modification. The Big Bang model might need significant changes. Our understanding of dark energy and dark matter might be wrong. It's not impossible. Science has been wrong before. But it would be the biggest shift in cosmology since the Big Bang theory itself. Explanation 5. We're measuring distances wrong. Maybe our distance measurements are off, and the structure isn't actually as large as we think. The problem? We measure cosmic distances using multiple independent methods, and they agree with each other. The redshift distance relationship is well established and tested. For the structure to be small enough to fit our models, our distance measurements would need to be wrong by a factor of 8. That would break basically all of cosmology. So, none of these explanations work perfectly, which brings us to the most unsettling possibility of all. Part 9. What if the universe isn't uniform? Let's talk about the cosmological principle again, because this is where things get philosophically weird. The cosmological principle states that on large scales, the universe looks the same everywhere and in all directions. This seems obviously true when you look at the night sky. Stars and galaxies are distributed pretty uniformly. The cosmic microwave background, the echo of the Big Bang, is incredibly uniform, varying by only 0.001% across the entire sky. Everything suggests uniformity. But here's the thing. We can only observe the observable universe. The entire universe is probably much, much larger than what we can see, maybe infinite. We're limited by the speed of light and the age of the universe. Light from beyond about 46 billion light years away hasn't had time to reach us yet. What if the observable universe just happens to be a relatively uniform patch, but the universe beyond is wildly different? Imagine you're a two-dimensional being living on the surface of a sphere, but you can only see a small patch around you. That patch looks flat. You'd conclude that the entire surface is flat. But you'd be wrong. You just can't see far enough to notice the curvature. What if we're in the same situation? What if the observable universe is just one region in a much larger, non-uniform cosmos? The Hercules-Corona Borealis Great Wall might be evidence of this larger scale structure. A hint that beyond what we can see, the universe is different than we thought. Some cosmologists have proposed that the universe might have a cellular structure on scales larger than we can observe. Regions of different density, different properties, separated by boundaries. We might be living in one cell, and the Great Wall might be part of the boundary to another cell. This is highly speculative. We have no direct evidence for it. But it would explain the observations. The counter-argument? If the universe is non-uniform at large scales, why is the cosmic microwave background so uniform? The CMB comes from the entire observable universe. If there were large-scale structures or non-uniformities, we should see them imprinted on the CMB. We don't. The CMB is uniform to 1 part in 100,000. Unless those structures formed after the CMB was emitted from initial conditions that were uniform but unstable. But that brings us back to the time problem. There hasn't been enough time. We're going in circles. Part 10. The Laniakea supercluster. a related mystery. While we're talking about giant cosmic structures, let me tell you about Laniakea. In 2014, astronomers mapped the motion of galaxies in our cosmic neighborhood. Not just their positions, but how they're moving. What they found was stunning. 100,000 galaxies, including the Milky Way, are all flowing toward a central region like rivers, flowing to the sea. This entire structure is called Laniakea, Hawaiian for immeasurable heaven. It's 520 million light-years across. That's under the theoretical limit, so it's not physics-breaking like the Hercules-Corona Borealis Great Wall. But here's what's interesting. We didn't know we were part of this structure until we mapped the motions. Looking at galaxy positions alone, Laniakea isn't obvious. It's only when you see the flow patterns, the velocities and directions galaxies are moving, that the structure reveals itself. What if there are other structures out there that we can't see yet because we haven't mapped the right properties? What if the Hercules-Corona Borealis Great Wall is just the part we can detect, and it's actually part of something even larger? The gamma-ray bursts might be tracing just one edge or one region of a structure that extends even further. That's a terrifying thought. Part 10, the Laniakea Supercluster, a related mystery. While we're talking about giant cosmic structures, let me tell you about Laniakea. In 2014, astronomers mapped the motion of galaxies in our cosmic neighborhood. Not just their positions, but how they're moving. What they found was stunning. 100,000 galaxies, including the Milky Way, are all flowing toward a central region like rivers flowing to the sea. This entire structure is called Laniakea, Hawaiian for immeasurable heaven. It's 520 million light-years across. That's under the theoretical limit, so it's not physics-breaking like the Hercules-Corona Borealis Great Wall. But here's what's interesting. We didn't know we were part of this structure until we mapped the motions. Looking at galaxy positions alone, Laniakea isn't obvious. It's only when you see the flow patterns, the velocities and directions galaxies are moving, that the structure reveals itself. What if there are other structures out there that we can't see yet because we haven't mapped the right properties? What if the Hercules-Corona Borealis Great Wall is just the part we can detect, and it's actually part of something even larger? The gamma-ray bursts might be tracing just one edge or one region of a structure that extends even further. That's a terrifying thought, because if we're missing structures this large, what else are we missing? Part 11, the dipole repeller and cosmic flows. Here's another piece of the cosmic puzzle that makes everything weirder. We know the Milky Way is moving, not just rotating, but traveling through space at about 600 kilometers per second. For decades, we thought this motion was caused by the Great Attractor, a massive concentration of mass pulling us toward it. But in 2017, researchers discovered something else, the dipole repeller. It's a vast void, a region with very little matter, that's effectively pushing us away from it. We're not just being pulled toward dense regions, we're being pushed away from empty regions. The combined effect of the Great Attractor pulling and the dipole repeller pushing explains our motion perfectly. But here's what this tells us. The universe has structure even in its empty spaces. The voids aren't just passive emptiness, they're active participants in cosmic dynamics. And these voids can be enormous. The Bode's void is 330 million light-years across, with almost no galaxies inside it. The voids, the filaments, the walls, they're all connected. They're all part of the same cosmic web. And if structures like the Hercules-Corona Borealis Great Wall exist, they're telling us that this web has larger scale patterns that we don't understand yet. Think of it like this. Imagine you're trying to understand a forest by looking at individual trees. You might notice that trees cluster together in groves. That's the galaxy cluster level. Then you zoom out and see that the groves form lines along ridges and valleys. That's the filament level. Zoom out further and you see the entire mountain range determining where forests can grow. That's the supercluster level. But what if you zoom out even further and discover the mountain range is part of a tectonic plate, and the plate boundaries determine where mountain ranges form? That's what these giant structures might be showing us. There's another level of organization we didn't know existed. Part 12. The axis of evil. Okay, buckle up because we're about to get into some controversial territory. Remember the cosmic microwave background? The afterglow of the Big Bang, which should be completely uniform and random? Well, there's a problem. In 2005, scientists analyzing CMB data noticed something weird. There were patterns in the temperature fluctuations that shouldn't be there. Specifically, some of the largest scale fluctuations seemed to align with each other. They called this alignment the axis of evil. Astronomers have a sense of humor. According to our models, the CMB fluctuations should be random. Any alignment should be purely coincidental. But the probability of this particular alignment happening by chance is about 1 in 1,000. Not impossible, but suspicious. And here's where it gets really weird. This axis seems to align with the plane of our solar system. Wait, what? How could the largest scale structure in the universe, patterns from the Big Bang itself, have anything to do with our tiny solar system? It shouldn't. It makes no sense. Unless it's not real. Maybe it's an artifact of how we measure the CMB. Maybe our instruments or our analysis methods are introducing this pattern. NASA and the European Space Agency have checked and rechecked. Different satellites, different instruments, different analysis methods. The axis persists. Now, most cosmologists think this is still just a statistical fluke. The universe is weird, and with enough data, you'll find weird coincidences. But some researchers have suggested something more radical. What if this axis indicates that the universe has a preferred direction? What if space itself has an orientation? This would violate the cosmological principle even more fundamentally than giant structures. It would mean the universe isn't isotropic. It doesn't look the same in all directions. And if that's true, pretty much all of cosmology needs to be rewritten. The connection to the Hercules-Corona Borealis Great Wall? Some researchers have noted that the Great Wall's orientation isn't random either. It seems to align roughly with other large-scale structures. Could these giant structures be evidence of the same underlying non-uniformity that creates the axis of evil? Maybe. Or maybe we're seeing patterns that aren't there, driven by our desire to make sense of confusing data. This is why science is hard. Part 13. Dark matter, dark energy, and cosmic structure. Let's talk about the invisible stuff that makes up most of the universe, because it's relevant to our giant structure problem. About 85% of the matter in the universe is dark matter. We can't see it directly. It doesn't emit or absorb light. We only know it exists because of its gravitational effects. Galaxies rotate too fast. The stars on the outer edges should fly off into space, but they don't. Something invisible is holding them together. That something is dark matter. Galaxy clusters move in ways that only make sense if there's way more mass than we can see. That extra mass is dark matter. The cosmic web itself, the filaments and walls, is shaped primarily by dark matter, with normal matter, stars, gas, planets, following along. When we talk about the Hercules-Corona Borealis Great Wall, we're really talking about a dark matter structure with galaxies embedded in it. The gamma-ray bursts we detect are coming from galaxies, which are trapped in the dark matter framework like flies in a spider's web. So the question becomes, what does dark matter do at these enormous scales? Our models of dark matter are based on observations at galaxy and galaxy cluster scales. We extrapolate those models to larger scales and assume dark matter behaves the same way. But what if it doesn't? What if dark matter has properties at supercluster scales that we don't understand? What if it clumps differently or interacts with itself in ways we haven't accounted for? This could potentially allow structures to form faster or grow larger than our current models predict. Then there's dark energy. Dark energy is even more mysterious than dark matter. It makes up about 70% of the universe's total energy and is causing cosmic expansion to accelerate. We don't know what it is. We just know it exists because galaxies are moving apart faster than they should be. Dark energy should work against structure formation. It's pulling space apart, making it harder for gravity to pull matter together. This is actually one reason why there's a limit to structure size. At large scales, dark energy's repulsive effect balances gravity's attractive effect. Structures can only grow until they reach a size where dark energy expansion counteracts gravitational collapse. So the Hercules-Corona Borealis Great Wall existing suggests either A, dark energy is weaker than we think, but we've measured it pretty accurately. B, dark energy wasn't always constant. It might have been weaker in the past. C, there's something about dark energy at large scales we don't understand. Option B is interesting. Some cosmological models suggest dark energy's strength might change over time. If dark energy was weaker in the early universe, structures could have grown larger before expansion started counteracting them. But this creates other problems with our models. We'd need to recalculate cosmic expansion history, reconsider Big Bang nucleosynthesis, re-examine the CMB predictions. It's complicated. Part 14, the biggest structure we've actually mapped. Let me tell you about something incredible. The largest 3D map of the universe ever made. The Sloan Digital Sky Survey, SDSS, has been mapping the universe for over 20 years. They've cataloged the positions and distances of millions of galaxies. In 2020, they released their latest results. They'd mapped 11 billion years of cosmic history, showing how structure evolved over time. What they found was both confirming and confusing. The cosmic web is real. The filaments, walls, and voids are everywhere, exactly as predicted. But the structures are bigger and more prominent than expected. There are more large-scale features than simulations suggested there should be. The SDSS data shows clear evidence of structures approaching and exceeding the theoretical limit. When you look at the map, You can see massive filaments connecting clusters and vast voids between them. It's beautiful and eerie at the same time. And here's what's really interesting. The map only covers a fraction of the sky. We've mapped maybe 30% of the observable universe in detail. What's in the other 70%? Probably more of the same, but also, possibly, more giant structures we haven't discovered yet. Every time we map a new region of space, we find more large structures. The Hercules-Corona Borealis Great Wall was discovered in gamma-ray data that covered a relatively small patch of sky. There could be dozens more structures like it that we simply haven't found yet because we haven't looked in the right places or with the right instruments. Part 15: Quasars and the Ancient Universe. Let's dive deeper into quasars because they're key to understanding these giant structures. Quasars are powered by supermassive black holes, typically billions of times the mass of the Sun. Matter falling into these black holes releases enormous energy. A single quasar can shine with the light of 1 trillion suns. Most quasars we observe are extremely distant, showing us the universe as it was billions of years ago. The furthest quasar we've found is about 13.1 billion light-years away. We're seeing it as it was when the universe was only 670 million years old. Wait, the universe was only 670 million years old, and supermassive black holes already existed? That's problematic. Supermassive black holes shouldn't form that quickly. According to our models, you need to start with a stellar black hole, formed from a collapsed star, then accumulate mass over billions of years to reach supermassive sizes. But these quasars existed when the universe was barely 500 million years old. There hasn't been enough time. Sound familiar? It's the same problem as the giant structures. Things exist that shouldn't have had time to form. Some researchers think these problems are connected. Maybe the early universe wasn't as uniform as we think. Maybe there were regions of higher density that allowed both supermassive black holes and large-scale structures to form faster. Or maybe our models of structure formation and black hole growth are missing something important. The large quasar groups, including the huge LQG, add another layer to this mystery. These are collections of quasars that are close together in space and exist at the same cosmic time. They mark regions where multiple supermassive black holes formed in proximity. This clustering suggests there's something special about these regions. More matter, more galaxies, more fuel for black holes. In other words, large-scale structures. The quasars are showing us where the biggest clumps of dark matter are, because that's where galaxies, and their central black holes, concentrate. And when we find large quasar groups spanning billions of light years, we're seeing evidence of dark matter structures spanning billions of light years. Part 16: The Trouble with Time. Let's get into the nitty-gritty of why time is such a problem for these structures. The universe began 13.8 billion years ago with the Big Bang. For the first 380,000 years, it was too hot and dense for atoms to form. Everything was a soup of particles and radiation. Then, at 380,000 years, the universe cooled enough for atoms to form. This is called recombination. Light could suddenly travel freely, and that light is what we now observe as the cosmic microwave background. At this point, the universe had tiny density fluctuations, regions that were 0.001% denser than average. These fluctuations were the seeds of all future structure. Over the next 13.8 billion years, these seeds grew through gravitational collapse. Denser regions pulled in more matter, becoming denser, pulling in more matter, etc. We can calculate exactly how fast this process happens. It depends on 1. The density of matter, which we know from multiple measurements. 2. The strength of gravity, which we know very precisely. 3. The expansion rate of the universe, which we've measured. 4. The dark energy effect, which we've measured. Put it all together, and you get a growth rate. In 13.8 billion years, starting from 0.001% fluctuations, structures can grow to about 1.2 billion light years before dark energy's expansion overwhelms gravity's attraction. That's the limit. It's not arbitrary. It comes from fundamental physics. For the Hercules-Corona Borealis Great Wall to exist at 10 billion light years, one of these factors must be wrong. Option 1, the initial fluctuations were larger, but we've measured them in the CMB. They were 0.001%, not 0.01%, not 0.1%, exactly 0.001% across the entire observable universe. Option 2, the growth rate is faster, but that would require either stronger gravity or different dark matter properties. Both would break other observations. Option 3, the universe is older, but we've measured the universe's age through multiple independent methods. Cosmic expansion rate, oldest stars, radioactive decay, CMB patterns. They all agree 13.8 billion years. Option 4, dark energy, was weaker in the past. This is actually possible. Some models allow dark energy to vary over time, but if dark energy was weak enough in the past to allow 10 billion light-year structures, it would change cosmic expansion history in ways that contradict other observations. Option 5, the structure formed through a different mechanism. Maybe these giant structures didn't form through normal gravitational collapse. Maybe they formed through some process we don't understand. But what process? Physics is physics. Gravity pulls things together. That's how structures form. What else could it be? This is the heart of the problem. Every solution creates more problems than it solves. Part 17, could we be wrong about the Big Bang? Okay, let's go there. What if the Big Bang model is wrong? I want to be clear. The Big Bang model is extremely well supported. It explains the cosmic microwave background, the abundance of light elements, hydrogen, helium, lithium, the expansion of the universe, the evolution of galaxies over time, the large-scale structure of the universe, mostly. Any alternative model would need to explain all of these things at least as well as the Big Bang does. That said, the Big Bang model has some problems. The horizon problem. How is the CMB the same temperature everywhere when distant regions couldn't have been in contact to equalize their temperatures? Solution? Cosmic inflation. A brief period of exponential expansion in the first fraction of a second. This solved the horizon problem, but introduced new questions. The flatness problem. Why is the universe's geometry so precisely flat? Solution. Also inflation. Inflation stretches space so much that any curvature becomes negligible. The monopole problem. Where are all the magnetic monopoles that should have formed in the early universe? Solution? Inflation again. It diluted the monopoles so much they're undetectable. Notice a pattern? Inflation solves all these problems, but we don't have direct evidence for inflation. We infer it must have happened because it solves problems. The giant structure problem is similar. We observe something that doesn't fit the model, so we need to either modify the model or find an explanation within the existing framework. Some alternative cosmological models have been proposed. Plasma cosmology. The universe is shaped by electromagnetic forces, not just gravity. This model struggles to explain the CMB and element abundances, so it's not widely accepted. Steady state theory. The universe has always existed and is constantly creating new matter. This was popular before the CMB was discovered, but the CMB's existence pretty much killed this model. Cyclic models. The universe goes through cycles of expansion and contraction. These models can be made consistent with observations, but they don't obviously solve the giant structure problem. Modified gravity. Maybe gravity works differently at very large scales. This could allow structures to form faster or grow larger, but any modification needs to be consistent with all other gravity observations, which is difficult. The truth is, the Big Bang model is probably mostly right. It works too well in too many areas to be fundamentally wrong, but it might be incomplete. Maybe there are processes or forces we don't understand yet that become important at the largest scales. Maybe the universe's properties vary in space or time in ways we haven't accounted for. The giant structures are telling us something. We just need to figure out what. Part 18. The observable universe versus the actual universe. Here's something that keeps me up at night. We can only observe a tiny fraction of the total universe. The observable universe, everything we could possibly see, extends about 46 billion light years in all directions. That's the distance light has had time to travel since the Big Bang, accounting for cosmic expansion. Beyond that, we have no idea. The universe could be infinite. It could be finite, but much, much larger than what we can see. It could have entirely different properties in regions beyond our cosmic horizon. Think about that. Everything we've ever observed, every star, every galaxy, the cosmic web, the giant structures, everything is just one region of possibly infinite space. What if the cosmological principle is true within our observable universe but breaks down at larger scales? What if there are structures so large that the observable universe is just a small part of them? The Hercules-Corona Borealis Great Wall is 10 billion light years across. The observable universe is 93 billion light years across. So the Great Wall is about 10% of the observable universe's diameter. That's like finding a building that's 10% as tall as the horizon is far away. It's huge, but it's not boundary-breaking huge. But what if the Great Wall continues beyond what we can observe? What if it's actually 50 billion light years across, or 100 billion, and we're only seeing a portion of it? We'd have no way to know. This is deeply unsettling from a scientific perspective. We can only make definitive claims about what we can observe. Everything beyond that is speculation, but it's also exciting. It means there's always more to discover. The universe is bigger and stranger than we can currently comprehend. Part 19. What would aliens see? Let's do a thought experiment. Imagine an alien civilization exists in a galaxy on the far side of the Hercules-Corona Borealis Great Wall. They look out at the universe with their telescopes. What do they see? Well, They'd see their local region of space. They'd map nearby galaxies, discover their own version of the cosmic web, measure cosmic expansion. If they're smart, they'd develop their own version of cosmology, their own models of structure formation. And here's the question: would they discover the same cosmological principle we did? Would they conclude the universe is homogeneous and isotropic at large scales? Or would their observations, from their particular vantage point, lead them to different conclusions? If the universe truly is homogeneous at large scales, then yes, aliens anywhere should discover the same principles. But if these giant structures are evidence of larger scale inhomogeneity, then different observers in different regions might see different things. An alien civilization in a massive void might conclude the universe is mostly empty with occasional clusters. An alien civilization in a dense supercluster might conclude the universe is mostly full of galaxies. Both would be looking at the same universe, just from different perspectives. This is called observer bias, and it's a real concern in cosmology. We assume our view of the universe is representative. But what if it's not? What if we happen to live in an unusual region? The anthropic principle suggests we might. We live in a region that's suitable for life, which might not be typical. Stars need certain conditions to form planets. Planets need certain conditions for life. Life needs billions of years of stability to evolve. These requirements might bias us toward living in atypically calm, stable regions of the universe. What if most of the universe is more chaotic, with larger structures and more extreme conditions? We'd never know, because we couldn't exist there to observe it. Part 20. The future of discovery. So where do we go from here? We've discovered structures that challenge our understanding of cosmology. What's next? Better surveys. The Vera Rubin Observatory, currently under construction, will survey the entire visible sky every few nights. It'll discover millions of new galaxies, quasars, and transient events. With that data, we'll be able to map large-scale structure in unprecedented detail. We might find more giant structures, or we might find that the Hercules-Corona Borealis Great Wall is an outlier and everything else fits our models. The Square Kilometre Array, this radio telescope currently being built in Australia and South Africa, will be 50 times more sensitive than any existing radio telescope. It'll be able to map the distribution of hydrogen gas throughout the universe, giving us a different view of cosmic structure. Hydrogen traces dark matter, so we'll be able to see the cosmic web's backbone more clearly. Gravitational wave. Astronomy. LIGO and Virgo have opened a new window on the universe. Future gravitational wave detectors will be able to observe mergers of supermassive black holes billions of light years away. This will give us information about the early universe and structure formation that we can't get from light alone. The James Webb Space Telescope, JWST, is already revolutionizing our view of the early universe. It can see further and more clearly than any previous telescope. It's finding galaxies that formed earlier than we thought possible, challenging our models of galaxy formation. As we gather more data on early galaxies and their distribution, we'll better understand how structure formed in the first billion years after the Big Bang. Better simulations. Computers are getting faster, and our cosmological simulations are getting more sophisticated. We can now simulate the entire observable universe at high resolution, tracking billions of dark matter particles and how they form structures. These simulations might reveal mechanisms for forming giant structures that we haven't considered. New physics. Maybe we need to modify our theories. Some physicists are exploring modifications to general relativity that might allow faster structure growth. Others are investigating whether dark matter has self-interactions we haven't accounted for. Still others are questioning whether dark energy is truly constant, or if it varies in space or time. Any of these could potentially explain the giant structures, but they'd need to be consistent with all other observations, which is the hard part. Part 21. The philosophical implications. Let's step back from the physics and think about what this means philosophically. For centuries, humans thought Earth was the center of the universe. Then we discovered we orbit the sun. Then we discovered the sun is one star among billions in a galaxy. Then we discovered our galaxy is one among billions in the universe. Each discovery made us smaller, less central, less special. This is called the Copernican principle. We don't occupy a special place in the universe. The cosmological principle is the Copernican principle on cosmic scales. Not only is our location not special, but all locations are equivalent. The universe looks the same everywhere. This is comforting in a way. It means the laws of physics we discover here apply everywhere. The universe is comprehensible and uniform. But the giant structures challenge this. If the universe isn't homogeneous at the largest scales, then maybe some regions are different from others. Maybe the laws of physics are the same everywhere, but the outcomes are different because initial conditions varied. Or maybe, and this is truly unsettling, the laws of physics themselves vary across cosmic scales or regions. We have some evidence this might be possible. The fine structure constant, which determines the strength of electromagnetic interactions, might vary slightly across the universe. If fundamental constants can vary, then different regions could have different physics. This would be both terrifying and exciting. Terrifying because it means the universe is more complex than we imagined, and our models might only apply locally. Exciting because it means there's so much more to discover, and the universe is weirder and more interesting than we thought. Part 22. What this means for us. Okay, let's bring this back down to Earth. Why should you care about giant cosmic structures 10 billion light years away? Fair question. They don't affect your daily life. They don't change gravity on Earth or alter the sun's behavior. But here's why it matters. Understanding our place in the universe. We're part of something incomprehensibly vast. The Milky Way is part of the local group, which is part of Laniakea, which is part of the cosmic web, which might be part of even larger structures we don't understand yet. Every human who ever lived, every story ever told, every war ever fought, every discovery ever made, it all happened in one tiny galaxy in this vast structure. That perspective is valuable. It makes our conflicts seem petty and our cooperation seem essential. The scientific method works. We discovered these structures by carefully observing the universe, analyzing data, and following the evidence wherever it leads. Even when the evidence contradicts our models, we don't ignore it. We try to understand it. This is science at its best. Humble in the face of reality, willing to revise theories when new data emerges. The fact that we can discover things that confuse us is a testament to the power of the scientific method. The universe is still mysterious. For all our progress, we still don't understand most of the universe. We don't know what dark matter is. We don't know what dark energy is. We don't know why the laws of physics are what they are. And now we've discovered structures that challenge our cosmological models. This means there's still so much to learn. The universe still holds surprises. For anyone who loves mystery and discovery, that's exciting. Technology drives discovery. We discovered these giant structures because we built better telescopes, better detectors, better computers for analyzing data. Every technological advance opens new windows on the universe. The same technologies we develop for astronomy often have applications on Earth. GPS relies on understanding relativity. Medical imaging uses techniques developed for astronomy. Pushing the boundaries of knowledge drives innovation. It might matter eventually. Right now, cosmology seems purely theoretical, but who knows what applications might emerge? Understanding cosmic structure could help us understand gravity better, which could lead to new technologies. Understanding dark matter and dark energy might unlock new physics with practical applications. Or maybe it won't. Maybe it'll remain purely theoretical forever, but that's okay too. Not everything needs to be useful. Some things are worth knowing just because they're true. Part 23. The actual discovery story. How we found it. Let me tell you the actual story of how the Hercules-Corona Borealis Great Wall was discovered, because it's a fascinating tale of detective work, pattern recognition, and scientific persistence. It starts in 1991, not with the Great Wall itself, but with the Compton Gamma Ray Observatory. This NASA satellite was designed to detect gamma ray bursts, those incredibly energetic explosions we talked about earlier. For 9 years, from 1991 to 2000, the Compton Observatory cataloged thousands of these bursts from all over the sky. Scientists weren't looking for giant cosmic structures. They were trying to understand gamma ray bursts themselves, what causes them, how they work, where they come from. By the early 2000s, we'd figured out the basics. Short-duration GRBS, less than 2 seconds, come from neutron star mergers. Long-duration GRBS, more than 2 seconds, come from massive stars collapsing into black holes. We also figured out how to measure their distances using their redshift, how much the light has been stretched by cosmic expansion. This was crucial. Before this, we knew where GRBs were on the sky, but not how far away they were. They could have been relatively close or incredibly distant. We had no way to tell. But by the mid-2000s, with better instruments and techniques, we could measure redshift for most GRBs. Suddenly, we had a 3D map of these explosions across cosmic time. Enter István Horváth, a Hungarian astronomer at the National University of Public Service in Budapest. In 2013, Horváth was analyzing a catalog of 283 gamma ray bursts that had well-measured redshifts. He wasn't looking for anything in particular. He was just exploring the data, looking for patterns. And he found one. There was a region of sky in the direction of the constellations Hercules and Corona Borealis where GRBs were clustering. At first, he thought it might be a measurement error or a selection effect. Maybe the telescope had observed that region more often, so naturally it found more GRBs there. But no. The coverage was uniform. This was a real concentration. He started calculating. If these GRBs were all at roughly the same distance, which their redshifts suggested they were, and they were clustering in space, then they must be part of some kind of structure. He ran statistical tests. What's the probability this clustering happened by random chance? About 1 in 20,000. That's not conclusive. In science, we usually want 1 in 3.5 million, 5 sigma confidence, before we claim a discovery. But it was intriguing enough to investigate further. Horvath contacted colleagues John Hakila at the College of Charleston and Zsolt Bogoli at Eötvös Loránd University. Together, they started a more detailed analysis. They looked at GRBS in the redshift range of 1.6 to 2.1, meaning these explosions occurred when the universe was between 3 and 4 billion years old, about 10 billion years ago in our time frame. Within this redshift slice, they found a striking concentration. Multiple GRBs clustered together in a region of space. They measured the size of this clustering. They calculated the structure's dimensions in 3 dimensions: right ascension, declination, and redshift distance. The answer they got was staggering, approximately 10 billion light-years across. They checked and rechecked. They tried different statistical methods. They looked for systematic errors. They tested whether this could be an artifact of how GRBs are distributed or detected. Every test confirmed it. There was a real structure there, and it was massive. In November 2013, they published their findings in the journal Astronomy and Astrophysics. The title of the paper was modest: Possible Structure in the GRB Sky Distribution at Redshift 2. But the implications were not modest at all. The astronomical community's reaction was mixed. Some astronomers were excited. This could be evidence of structure formation processes we don't understand. It could reveal something fundamental about the early universe. Others were skeptical. Extraordinary claims require extraordinary evidence, and a statistical significance of 1 in 20,000 wasn't extraordinary enough for some. Critics pointed out that with thousands of GRBs in the catalog, you'd expect to find some clusters just by chance. Maybe this was one of those random clusters. Horvath and his team countered. They'd tested for this. They'd run simulations of random GRB distributions and found that clusters this size and density were indeed extremely rare. The debate continued for years. Then, in 2015, more data became available. NASA's SWIFT satellite had detected hundreds more GRBS with measured redshifts. Horvath's team reanalyzed the structure with the new data. It was still there. The clustering persisted. With more GRBS in the catalog, the statistical significance actually increased. By 2015, the probability of this clustering being random chance had dropped to about 1 in 200,000. Still not the gold standard 1 in 3.5 million, but increasingly difficult to dismiss as a fluke. Other research groups started looking at the data independently. Some confirmed the finding. Others found the evidence less convincing. This is how science works. A discovery is made, it's published, other scientists scrutinize it, some confirm it, some challenge it, and gradually a consensus forms, or doesn't. As of now, the consensus is, there's probably something real there. But we need more data to be certain. The Hercules-Corona Borealis Great Wall is in a weird state of scientific limbo. It's likely real, but not definitively confirmed. And that's okay. Science can live with uncertainty while we gather more evidence. Part 24. The gamma-ray burst connection. Why these explosions matter. Let's dive deeper into why gamma-ray bursts are such useful tools for mapping the universe, because this is actually pretty clever. Gamma-ray bursts are among the most luminous events in the universe. For a few seconds to a few minutes, a single GRB can outshine billions of galaxies combined. This extreme brightness means we can see them from enormous distances, across billions of light years, all the way to when the universe was young. The most distant GRB ever detected, GRB 090429b, occurred when the universe was only 520 million years old, about 13.1 billion years ago in our time frame. Think about that. We're detecting individual stellar explosions from when the universe was barely 4% of its current age. No other astronomical phenomenon gives us this kind of range. Supernovae are bright, but not bright enough to see across most of the universe. Quasars are bright and distant, but they shine continuously, making it harder to measure exact distances. GRBS are perfect, incredibly bright, brief, so we can time them precisely, and they occur in star-forming galaxies, so they trace where matter is concentrated. When we detect a GRB, we can measure its redshift, how much the wavelength of its light has been stretched by cosmic expansion. Redshift tells us distance. The more stretched the light, the farther it traveled, the longer ago it was emitted. For the GRBS in the Hercules-Corona Borealis Great Wall, the redshift is around 1.6 to 2.1. This corresponds to light travel time of about 10 billion years. These explosions happened 10 billion years ago, when the universe was 3 to 4 billion years old. But here's the cool part. We can also measure the GRB's position on the sky very precisely. Combine position with distance, and you have a 3D coordinate. You know exactly where in space that explosion occurred. Do this for hundreds or thousands of GRBs, and you're mapping the distribution of star-forming galaxies across cosmic time. Regions where GRBs cluster are regions where many star-forming galaxies exist close together. And regions with many galaxies close together indicate underlying dark matter structures, filaments and walls in the cosmic web. The Hercules-Corona Borealis Great Wall showed up as a clustering of GRBS because it's a region of space where dark matter concentrated, pulling in gas, forming galaxies which formed stars, some of which exploded as GRBs. The GRBs are just the visible tracers of an invisible structure. It's like using fireflies to map a forest at night. The fireflies cluster where trees provide habitat. The GRBs cluster where dark matter provides gravitational wells. This technique, using transient events to map cosmic structure, is brilliant and relatively new. Before we could measure GRB distances reliably, we couldn't do this. Now we can, and we're discovering things about the universe's structure that we couldn't see any other way. Part 25. Other record-breaking structures. The Hercules-Corona Borealis Great Wall isn't the only structure that's challenged cosmological models. Let's talk about the other giants. The Sloan Great Wall, 2003. Discovered in the Sloan Digital Sky Survey data, this structure is about 1.37 billion light-years long. It's a vast filament of galaxies forming a wall-like structure. When discovered, it was the largest known structure in the universe. 1.37 billion light-years is already over the theoretical 1.2 billion light-year limit, so this was the first structure to raise serious questions about cosmological models. The Sloan Great Wall exists relatively nearby in cosmic terms, only about 1 billion light-years from Earth, meaning we're seeing it as it was 1 billion years ago. The huge LQG 2012. The Huge Large Quasar Group is a collection of 73 quasars forming a structure about 4 billion light-years across. This was discovered by analyzing the positions of quasars in the Sloan Digital Sky Survey. 4 billion light-years. That's more than 3 times the theoretical limit. The odds of 73 quasars clustering this tightly by random chance are astronomically small, less than 1 in a billion. The huge LQG exists about 9 billion light-years away, showing us the universe when it was less than 5 billion years old. At that age, structures this large simply shouldn't have had time to form yet. The giant GRB ring, 2015. This structure, discovered in gamma-ray burst data, is about 5.6 billion light-years across. It's arranged in a ring or circle-like pattern, which is unusual. Most large structures are filamentary or sheet-like. The ring contains 9 GRBC at roughly the same distance from us, arranged in a circular pattern on the sky. 5.6 billion light-years, nearly 5 times the theoretical limit. This discovery was particularly controversial because the pattern seemed almost too regular. Could it be a statistical artifact? Multiple independent analyses confirmed it's likely real, though some astronomers remain skeptical. The Giant Arc, 2021. This is one of the most recent discoveries. It's a giant arc of galaxies spanning 3.3 billion light-years, located about 9.2 billion light-years from Earth. What makes this interesting is its shape. It curves in a huge arc across the sky, visible as a concentration of galaxies and galaxy clusters. The astronomer who discovered it, Alexia Lopez, was analyzing galaxy distribution data when she noticed this curved pattern. 3.3 billion light-years is about 2.75 times the theoretical limit. And here's the kicker. There's another large structure nearby called the Giant Arc's neighbor, roughly the same size. 2 giant structures close to each other, both over the size limit. This suggests these aren't just random flukes. There might be physical processes creating structures at these scales that we don't understand. Common patterns. All of these structures share some characteristics. 1. They're all discovered in different ways: galaxy surveys, quasar catalogs, GRB data, suggesting this isn't an artifact of one particular observation method. 2. They all exist at high redshift, meaning they formed when the universe was young, which makes them even more problematic because there was even less time for structure formation. 3. They're all multiple times larger than the theoretical limit, not just slightly over it. 4. They all have statistical significance high enough that random chance is unlikely, though not impossible. This pattern suggests something systematic is going on. We're not just finding 1 or 2 outliers, we're finding multiple structures across different cosmic eras and different types of astronomical objects. Either we're incredibly unlucky and keep finding statistical flukes, or there's something wrong with our models. Part 26. The role of computer simulations. Let's talk about how we know what structures should look like, because this involves some of the most massive computational efforts in science. Cosmological simulations try to recreate the universe on computers. They start with the conditions right after the Big Bang, a nearly uniform distribution of dark matter with tiny fluctuations. Then they run the physics forward. They simulate how gravity pulls matter together, how dark matter clumps, how gas flows into dark matter halos, how stars form, how galaxies evolve. The largest simulations track billions of particles representing dark matter and gas, simulating cubic regions of space, hundreds of millions of light years across. These simulations take months to run on supercomputers, using thousands of processors simultaneously. The result is a detailed prediction of what cosmic structure should look like at different times in the universe's history. And here's the amazing part. The simulations match observations incredibly well. The cosmic web, filaments, walls, voids, all emerge naturally from the simulations. You don't have to program in make filaments. You just simulate gravity acting on matter, and filaments form automatically. The distribution of galaxy masses, the clustering patterns, the relationship between dark matter and visible matter, all match observations. This is why cosmologists are confident in the standard model. The simulations work. Except, when you measure the largest structures in simulations and compare them to the theoretical limit, they agree. Structures in simulations rarely exceed 1.2 billion light-years. The simulations don't produce structures as large as the Hercules-Corona Borealis Great Wall. So either A, the simulations are missing some physics that allows larger structures to form. B, the observed structures aren't real, they're statistical flukes or measurement errors. C, the simulations are correct, and the structures are rare outliers, unlikely but not impossible. Most cosmologists lean toward option C. The structures are real but rare, and we've been lucky, or unlucky depending on your perspective, to find several of them. But some researchers argue for option A. Maybe there's feedback between dark matter and dark energy we haven't modeled correctly. Maybe the initial conditions had larger fluctuations in some regions. Maybe there's physics we're missing. The way to resolve this is to run more detailed simulations and gather more observational data. The next generation of simulations will track even more particles, simulate larger volumes of space, and include more physics, magnetic fields, cosmic rays, black hole feedback, etc. If these improved simulations start producing larger structures that match observations, we'll know we were just missing some details. If they don't, we'll know something more fundamental is wrong. Part 27. The measurement challenges. Let me talk about how difficult it is to actually measure these structures, because it's not as straightforward as you might think. When you look at the sky with a telescope, you're getting a 2D projection. You can measure an object's position, coordinates on the sky, but not its distance directly. To get distance, you need redshift. Redshift is measured by looking at spectral lines, specific wavelengths of light emitted by atoms. In a stationary source, these lines occur at specific known wavelengths. But if the source is moving away from us due to cosmic expansion, the light gets stretched, shifting to longer, redder wavelengths. The amount of shift tells you how fast the source is receding, which tells you how far away it is. This works well for individual objects, But what if you want to map the structure of a billion light-year wide region? You'd need redshifts for thousands of objects in that region. For galaxies, this means pointing a telescope at each one, collecting enough light to see spectral lines, and measuring the redshift. This is incredibly time-consuming. Even the largest galaxy surveys take years to map millions of galaxies. For gamma-ray bursts, it's even harder. GRBS are transient. They fade within hours or days. You have to detect them quickly, point a telescope at them immediately, and get a spectrum before they disappear. Many GRBS fade too quickly to get good redshift measurements. Others occur during satellite downtime, or in regions of sky that aren't visible to follow-up telescopes. Of the thousands of GRBs detected, only a few hundred have reliable redshift measurements. This small sample size creates statistical challenges. Are we seeing real structures, or are we seeing patterns in noise? This is why the Hercules-Corona Borealis Great Wall's statistical significance is only 1 in 20,000 to 1 in 200,000. With a small sample, it's hard to be more certain. As we detect more GRBs and measure more redshifts, the statistics will improve. Another challenge: measuring the structure's size. A structure isn't a well-defined thing. It's not like there's a sharp boundary where it starts and stops. The Hercules-Corona Borealis Great Wall is a region where GRBs are more concentrated than average. But how much more concentrated? And how do you define the edge? Different researchers using different statistical methods get different size estimates for the same structure. Some measurements put the Hercules-Corona Borealis Great Wall at 6 billion light-years, others at 10 billion, others at 12 billion. All agree it's massive, but the exact size is uncertain. This uncertainty doesn't mean the structure isn't real. It just means measuring structures this large is genuinely difficult. Part 28. What this means for the fate of the universe. Let's get existential for a moment and talk about how these giant structures might affect the universe's long-term fate. The universe is expanding, and that expansion is accelerating due to dark energy. In the far future, trillions of years from now, this acceleration will have dramatic effects. Galaxies outside our local group will recede so fast that their light will never reach us. The observable universe will shrink. Eventually, only our local group of galaxies will be visible. Trillions of years after that, the universe will expand so much that even atoms might be torn apart in what's called the Big Rip. This is the standard fate of the universe according to current models. But this assumes the cosmological principle is correct and dark energy is constant. If the Hercules-Corona Borealis Great Wall indicates the universe is non-uniform at large scales, or if dark energy varies in space or time, then the universe's fate might be different. In regions where dark energy is weaker, gravity might eventually overcome expansion, causing those regions to collapse. In regions where dark energy is stronger, expansion might accelerate even faster. The universe could fragment into regions with different fates. This is highly speculative. We have no evidence dark energy varies this way, but the existence of structures that challenge our models opens the possibility. Another consideration: if structures can be larger than we thought, then gravity's influence extends further than we thought. The Great Wall, if it's gravitationally bound, meaning its parts are held together by gravity, would have significant gravitational effects on surrounding regions. It might pull on nearby galaxy clusters, affecting their motions in ways we haven't accounted for. This could influence how we measure cosmic expansion, potentially affecting our understanding of dark energy. Some researchers have suggested that unaccounted for large-scale structures could be causing apparent anomalies in cosmic expansion measurements. This is controversial and unproven, but it's an example of how giant structures could have implications beyond just being big. Part 29. The human element. Why scientists care. I want to talk about the humans behind this discovery because science isn't just cold data and equations. It's done by passionate people driven by curiosity. Istvan Horvath, the lead discoverer of the Hercules-Corona Borealis Great Wall, has spent years defending his finding against skeptics. In interviews, he's described the mixture of excitement and frustration. Excitement at finding something potentially groundbreaking. Frustration when other scientists dismiss it as a statistical fluke. This is normal in science. Big claims face big skepticism, as they should. Horvath and his colleagues have responded by gathering more data, refining their statistics, and engaging with critics. They believe in their discovery, but they're not dogmatic. If better data disproves the structure, they'll accept it. That's the scientific mindset, committed to finding truth, not to being right. Other astronomers working on large structures have similar experiences. Alexia Lopez, who discovered the giant arc, was a PhD student when she made her finding. Imagine being in your 20s and discovering something that challenges the foundations of cosmology. That's simultaneously thrilling and terrifying. In interviews, she's described the moment she realized the pattern in her data was real, not a mistake. The rush of excitement followed by immediate doubt. Am I seeing what I think I'm seeing? Then the careful work of checking and rechecking before telling anyone. Then the nerve-wracking process of writing it up and submitting it to a journal, knowing it will be scrutinized intensely. Then the publication and the media attention, and having to defend your work to established professors who've been in the field for decades. This is science at the frontier. It's exciting, but it's not easy. These researchers are driven by a fundamental human urge, the desire to understand. What's out there? How does it work? What does it mean? These questions have driven human inquiry for millennia. The tools and methods have changed, but the core motivation hasn't. And when you discover something that might rewrite our understanding of the cosmos, that's one of the peak experiences a human can have. That's why scientists care about giant cosmic structures. Not because they're useful, not because they'll make money, but because they're mysterious, and understanding them means understanding the universe a little bit better. And understanding the universe is, in a way, understanding ourselves, because we're made of the same atoms, governed by the same physics, shaped by the same cosmic history. Part 30. The next generation of telescopes and what they'll reveal. The good news is that we're about to enter a golden age of observational cosmology. New instruments coming online in the next few years will revolutionize our ability to map cosmic structure. The Vera Rubin Observatory. This telescope in Chile will start operations in 2025. It has a camera with 3.2 billion pixels, the largest digital camera ever built for astronomy. Every few nights, it will photograph the entire visible sky, over and over again. Within 10 years, it will have created the deepest, most comprehensive map of the universe ever made. It will detect billions of galaxies, millions of transient events, thousands of new asteroids, supernovae, and variable stars. For our purposes, it will map large-scale structure with unprecedented detail. If there are more structures like the Hercules-Corona Borealis Great Wall, Vera Rubin will find them. It will also provide statistics. How common are these giant structures? Are they rare outliers or more common than we thought? With billions of galaxies mapped, we'll finally have the sample size to answer these questions definitively. The Square Kilometre Array. This radio telescope is being built across sites in Australia and South Africa. When complete, it will be 50 times more sensitive than any existing radio telescope. It will map the distribution of neutral hydrogen gas throughout the universe. Hydrogen is everywhere. It traces dark matter structures even in regions where stars haven't formed yet. This means the SKA will see parts of the cosmic web that are invisible to optical telescopes. It might reveal dark matter filaments we didn't know existed. It might show that structures like the Great Wall are even larger than we thought, extending into regions where there aren't many visible galaxies. The Nancy Grace Roman Space Telescope. NASA's next flagship space telescope after James Webb, Roman will launch in 2027. It has a field of view 100 times larger than Hubble's. It will survey vast areas of sky in unprecedented detail. Its main science goals include mapping dark matter and dark energy, but in doing so, it will create detailed 3D maps of cosmic structure. Roman will be particularly good at finding distant galaxies and measuring their redshifts efficiently. This means better maps of the early universe, showing us how structure formed when the cosmos was young. Improved GRB detection. Future gamma-ray satellites will detect more GRBs with better precision. The Einstein probe, launched by China in 2024, is already detecting more transient events. The SVOM satellite, Space-Based Multiband Astronomical Variable Objects Monitor, a French-Chinese collaboration, is dedicated to GRB detection and rapid follow-up. With more GRBs detected and more redshifts measured, we'll have better statistics on structures like the Hercules-Corona Borealis Great Wall. We'll be able to map it in more detail, determine if it's part of something larger, and see if similar structures exist elsewhere. Gravitational wave cosmology. This is a newer field, but it's promising. When black holes or neutron stars merge, they create ripples in space-time, gravitational waves that we can detect. LIGO and Virgo have already detected dozens of these mergers. Future detectors like the Einstein telescope, planned for the 2030s, will be much more sensitive. They'll detect mergers from across the universe, giving us another way to map cosmic structure. Gravitational waves carry different information than light. They're not blocked by dust or gas. They propagate directly from their sources to us. This gives us an independent check on our maps, made from light-based observations. If gravitational wave observations confirm the large structures we see in electromagnetic observations, we'll be more confident they're real. Machine learning and big data. As telescopes collect more data, human astronomers can't analyze it all manually. This is where artificial intelligence comes in. Machine learning algorithms can search through millions of galaxy images, looking for patterns humans might miss. They can identify clusters, filaments, and voids in 3D galaxy distribution data. They can find anomalies, regions where structure is unusual or unexpected. Several research groups are already using neural networks to analyze cosmological survey data. These algorithms have found structures humans overlooked and confirmed structures humans suspected but couldn't verify statistically. As AI improves, it will become an essential tool in cosmic cartography. Part 31: The broader implications for physics. Let's zoom out and think about what these giant structures mean for physics as a whole. Testing general relativity at cosmic scales. Einstein's theory of general relativity describes how gravity works. It's been tested extensively at solar system scales, planetary orbits, gravitational lensing, and at galaxy cluster scales, gravitational lensing, cluster dynamics. But at the scale of superclusters and giant walls, testing becomes difficult. The existence of structures larger than predicted might indicate that general relativity needs modification at these scales. Some physicists have proposed modifications to general relativity that change how gravity behaves over extremely large distances. These modified gravity theories can potentially explain both dark energy and faster structure formation. If they're correct, we wouldn't need dark energy at all. The accelerating expansion would be a consequence of modified gravity. Giant structures could be evidence for modified gravity, though this is far from proven. The nature of dark matter. We know dark matter exists, but we don't know what it is. The leading candidate is WIMPs, weakly interacting massive particles, hypothetical particles that only interact through gravity and possibly the weak nuclear force. But despite decades of searching, we haven't detected WIMPs directly. Some physicists propose alternatives: axions, sterile neutrinos, primordial black holes, or more exotic options. Different types of dark matter would cluster differently, forming different large-scale structure patterns. If dark matter has self-interactions, meaning dark matter particles can interact with each other, not just through gravity, this could affect how large structures can grow. The existence of giant walls might tell us something about dark matter's properties. For example, if dark matter is warm rather than cold, meaning particles move faster, it would resist clustering at small scales, but might allow larger structures to form. Detailed observations of structures like the Hercules-Corona Borealis Great Wall could help discriminate between dark matter models. Quantum origins of cosmic structure. Here's something wild. The largest structures in the universe ultimately originated from quantum fluctuations. In the first fraction of a second after the Big Bang, during cosmic inflation, quantum fluctuations in the inflaton field, the field driving inflation, were stretched to cosmic sizes. These fluctuations became the density variations that eventually grew into galaxies, clusters, and larger structures. Quantum mechanics operating at the smallest scales created structure at the largest scales. If we find structures larger than our models predict, it might tell us something about the physics of inflation or the quantum fluctuations that seeded structure. Maybe the fluctuations were larger in some regions. Maybe inflation lasted longer in some places. Maybe the quantum field had properties we haven't accounted for. Cosmic structure is a window into quantum gravity, the still unsolved problem of how to combine quantum mechanics and general relativity. The multiverse connection. Some theories of cosmic inflation predict a multiverse, an infinite number of separate universes, each with potentially different properties. In a multiverse scenario, the cosmological principle might only apply within each universe, not across the entire multiverse. Our observable universe might be one region of one universe in the multiverse. If so, what we call the universe might not be homogeneous beyond what we can observe. The Hercules-Corona Borealis Great Wall could be evidence of larger scale structure that extends beyond our observable patch. This is highly speculative, but it demonstrates how observations of large-scale structure connect to the deepest questions in theoretical physics. Part 32. What students and young scientists are discovering. One thing I find inspiring about this field is how many important discoveries are made by graduate, students, and early career researchers. Alexia Lopez discovered the giant arc as a PhD student. Many of the researchers analyzing GRB distributions and finding large structures are in their 20s and 30s. This isn't unusual in astronomy. Young scientists often make breakthroughs because they 1. Have fresh perspectives, unbiased by decades of expecting certain results. 2. Are willing to try new analysis methods and unconventional approaches. 3. Have the energy and time to dig through massive datasets looking for anomalies. 4. Ask questions that established scientists might consider naive, but turn out to be profound. The Hercules-Corona Borealis Great Wall was found by researchers willing to ask, what if we map GRB distributions and see what patterns emerge? That seems obvious in retrospect, but it wasn't until someone actually did it that we discovered this structure. There are probably more discoveries waiting in existing data, waiting for someone to ask the right question or look at the data in the right way. This is exciting for anyone considering a career in science. You don't need to be Einstein to make important discoveries. You need curiosity, persistence, and willingness to follow evidence wherever it leads. The next major breakthrough in cosmology might come from someone reading this right now, who decides to study physics or astronomy and eventually analyzes data in a novel way. Part 33. The public response and science communication. When the Hercules-Corona Borealis Great Wall was announced in 2013, it made headlines. Biggest structure in universe discovered ran articles in major news outlets. The public response was fascinating. Many people were awed. The scale of the structure, 10 billion light years, captures the imagination in a way that technical details about cosmological models don't. Some people were confused. How can we see something 10 billion light years away? Does that mean it's 10 billion years old? Yes, we see it as it was 10 billion years ago, because light from it took 10 billion years to reach us. Some people asked, how do we know it's still there? We don't. It's probably still there. Structures this large don't change much in mere billions of years, but we're seeing ancient history, not the present. This highlights a challenge in science communication. Cosmology deals with scales and concepts that are profoundly counterintuitive. Light travel time, cosmic expansion, redshift, the difference between distance and look-back time. These aren't everyday concepts. Explaining them clearly without oversimplifying is difficult, but important, because the public funds much of this research through government science agencies. Scientists have a responsibility to explain what they're discovering and why it matters. The Hercules-Corona Borealis Great Wall matters because it challenges our understanding of the universe. That might seem abstract, but understanding the universe is a fundamentally human endeavor. Every culture throughout history has created cosmologies, explanations for what the universe is and how it works. Modern cosmology is humanity's current best answer to these ancient questions, refined by the scientific method. When we discover something that doesn't fit our models, we're not just finding an anomaly in data. We're finding a crack in our current understanding, an opportunity to develop a deeper, more accurate picture of reality. That's worth funding. That's worth celebrating. Conclusion. Part 2. The beauty of uncertainty. We've reached the end of this journey through cosmic structure, and I want to leave you with a thought that's guided my entire approach to this topic. Science isn't about certainty. It's about increasingly accurate approximations of truth, refined through observation and evidence. The Hercules-Corona Borealis Great Wall presents us with uncertainty. We're fairly confident it exists. The statistical evidence is strong, though not overwhelming. We're uncertain what it means. Does it violate the cosmological principle, indicate modified gravity, reveal dark matter properties, or simply represent a rare but allowed fluctuation in structure formation? We don't know, and that's okay. In fact, that's beautiful, because uncertainty drives discovery. If we knew everything, there would be nothing left to explore. The Great Wall is an invitation. It's the universe saying, "You think you understand me? Look at this. Explain this. There's more here than you realized." Some scientists find uncertainty frustrating. They want answers, not questions. But the best scientists, in my view, embrace uncertainty. They see it as opportunity. Every unexplained observation is a chance to learn something new. Every anomaly is a potential breakthrough. The Hercules-Corona Borealis Great Wall might be explained within our current models. It might require minor modifications. Or it might require a fundamental rethinking of cosmology. We won't know until we gather more data, develop better theories, and test them rigorously. That process will take years, probably decades. But that's science. It's patient. It's careful. It builds knowledge brick by brick, refining understanding through generations of researchers. We're part of that process. Everyone who's ever looked up at the night sky and wondered what's out there is part of humanity's long journey to understand the cosmos. The Hercules-Corona Borealis Great Wall is the newest chapter in that story. It's not the final chapter. There will be more discoveries, more surprises, more mysteries revealed. The universe is vast beyond comprehension, complex beyond imagination, strange beyond expectation. And we're here, on a small planet orbiting an average star in an ordinary galaxy, trying to understand it all. That's ambitious, maybe hubristic, but it's also magnificent. We've come so far from thinking Earth was the center of everything to knowing we're a tiny part of a structure 10 billion light years across. From believing the universe was static and eternal, to understanding it's expanding and evolving. From thinking the Milky Way was the entire universe, to knowing there are hundreds of billions of galaxies in structures that span cosmic scales. Every step of that journey involved someone making an observation that didn't fit existing models. The Hercules-Corona Borealis Great Wall is the latest such observation. What will we discover next? What will future telescopes reveal? What will the next generation of scientists uncover? I don't know, but I'm excited to find out. And I hope you are too, because this is humanity's grandest adventure, the quest to understand the universe and our place in it. The Hercules-Corona Borealis Great Wall is a signpost on that journey, pointing toward mysteries yet to be solved, the biggest thing in the universe. For now, who knows what we'll find? Tomorrow,